Hello, and welcome to our fourth lesson in our Generative AI course for founders and investors. In this lesson, we're going to explore how to develop your own generative AI system. This won't be a deep dive into everything you need to know, but we will cover high-level topics that can give you insights into key pieces of the system. You'll then be able to explore these topics deeper, hopefully guided by our discussion here. Now, as we discussed in our competitive advantage section, these models are extremely expensive to train, and if you're hoping to train your own model from scratch, you will need to do a fair bit of work raising capital for compute and putting together a team. However, as of today, you can still build specialized generative models for under 100 grand that will work well for your niche of interest, such as music generation or medical document creation. In order to train or fine-tune a generative AI model, it is essential to choose the right dataset. The dataset should be large enough and diverse enough to provide the model with enough data to learn from, and the data should be relevant to the task at hand. So, for example, if you're trying to train a generative model to generate cat images, you need a dataset of cat images. The first step is collection. In order to curate or collect the dataset, you need to identify first the modality of data. Are you working with images? Are you working with text? And you'll need to find sources for that data. This could be scraping the internet. This could be purchasing some selection of documents. So if, for example, you're trying to train a generative AI system for sales and outreach emails, you would first need to collect some documents, emails, and factual sources relating to sales broadly and to your specific product. You would then automate this collection process using web scraping or existing APIs. After the dataset is collected, you will need to curate that dataset. The curation happens via filtering. There are several ways to filter this data. We're going to talk about one that's extremely powerful. It is a little bit complicated, but it's so powerful that I think we need to spend some time thinking about how it works. Of course, filtering needs to happen automatically because there's usually too much data for you to sort by hand. If you did have enough people, then maybe you could train humans to mark the data as high or low quality, but that is quite expensive. So instead, you or the founder of the company will label a small subset of the data by hand, or you can pseudo-label the data by selecting it from a source that you trust, like Wikipedia, or maybe a certain medical journal. You will then train a classifier, typically logistic regression, to predict whether some piece of data, some piece of content, belongs to your high-quality set. What you can then do is run that classifier on all of your data and filter based on confidence. The classifier will give you a probability of whether that data is high quality or low quality, and you can set a threshold. This is what was done as part of the training for GPT-3, Codex. Lots of systems do this. DeepMind does this with their systems. There's also some other filters that you need to do, such as removing extremely short documents or removing documents with mostly random content. So once you've created a suitable data set, you'll need to choose an appropriate architecture for your model. This choice will depend on the specific task that you're trying to accomplish, as well as the type of data you're working with. So, for example, if you're working with images, you'll need to use something like a convolutional neural network. If, however, you're working with language, you'll want to use something like a transformer. It really is modality dependent in this case. There are many benchmarks on papers with code that you might find extremely interesting. Now let's say you're working with language. You do want to use a transformer, but you'll need to decide if you want a GPT style, a BERT style, T5, or some other type of transformer model. The Hugging Face documentation is actually a great resource for determining the type of model that you should use. My opinion, at least, is by default for generative tasks, I would probably use some GPT-Neo model or GPT-J. However, Flan T5 XXL is also an excellent choice for start. In general, this is a difficult and nuanced decision, and there are many models to choose from. But luckily, a lot of these models all perform quite well. And so it's hard to go wrong with your first choice as long as the modality is correct. If you want a more detailed guide, feel free to reach out. I'm happy to answer your questions if you give me a brief description of your problem. So, something important to note before we dive into training, I should say that there is, in general, a very large engineering challenge getting the compute in order. You'll need dozens or even hundreds of GPUs just to fine-tune some of these models with a few billion parameters. Unfortunately, we don't have the time or the space to dive into that portion of the setup, except I will just mention that there are teams at various cloud providers who are eager to help startups get running on their infra. So you should lean on those teams when you can. Now, once you have chosen the dataset and architecture for your generative AI model, you can begin the process of training and fine-tuning. Training and fine-tuning are essentially equivalent, but the hyperparameters, such as learning rate, might be slightly different. Now, it is mostly a spectrum between full training, sometimes called pre-training, and the partial fine-tuning process. In general, however, you are likely to be using a model that was already trained and just fine-tuning it to your specific task, unless you're hoping to train your own foundation model, which is beyond the scope of this course. The fine-tuning process involves feeding the model the training data and then adjusting the model's parameters based on how well it learns from the data. So one common approach to training and fine-tuning a generative AI model is to use a technique that we've already talked about called gradient descent, which updates your model's parameters stochastically. We talked about this a little bit in lesson 2, so I won't go into that here. Many of these models require, like I said, an enormous amount of compute. The Chinchilla paper from DeepMind suggested that GPT-3 was actually undertrained by many orders of magnitude. This means that the 300 billion tokens that it did see was insufficient, and it should have seen potentially well over 1 trillion words. This implies, however, that we can train smaller models for much longer, and it actually achieves similar performance to much larger models that have been undertrained. So what I mean to say there is, if you are training a model, you can get away with a smaller model trained on more data. Interestingly enough, many of the recent results and amazing applications we have seen are limited by the pure fact that people are only willing to wait about a month for a model to train. Now, let's dive into evaluation. Once you've trained and fine-tuned your generative AI model, you'll need to evaluate its performance. This is how well the model performs on generating new or original data. Additionally, if you have a set of foundation models you're trying to evaluate against each other, it is also important to be able to empirically look at their performance. So there are a number of different metrics and techniques that can be used to evaluate the performance of generative AI models. Depending on the specific task you're working on, will determine which of these metrics you should choose. So for example, if you're working on images, you might want to use a technique that measures image quality automatically, like FID or clip metric. Alternatively, you could hire human evaluation to assess the preferred quality of your generated images. Many systems, as I mentioned, pay human raters to give their preference on the set of images, and then use a percentage of images that were preferred as the metric. There are other automated ways, such as training a classifier, to tell between real and fake images, somewhat similar to a generative adversarial network. This goes beyond just pure accuracy. Because we are generating data, it is hard to evaluate whether we got the generation correct or incorrect. And so the models and the metrics we're describing here are measuring quality in some sense. So for take language, for example. You might use a metric like perplexity or BLUE score to evaluate the quality of the generated text. Perplexity can be thought of as the model's surprise at seeing a set of words. So for the phrase, "I like to eat," a word pie might have very low perplexity, while something like dirt would have a higher perplexity. This means that if your model is good at generating text, it will have a lower perplexity for human written text. The blue score, on the other hand, or the bilingual evaluation understudy score, is a metric used to evaluate the quality of text generated by some generative model. It's somewhat complicated. The jargon is that it compares the generated text with some set of reference text and calculates the proportion of n-grams, or sequences of words, that are present in both the generated and reference translations. So the higher the blue, the more similar the generated text is to the reference translation, and therefore the better the model is at matching human text. Blue is often used in machine translation, but it can be used for other natural language generation tasks. So in summary, by carefully evaluating the performance of your generative AI model, you can determine whether it is performing well and ready for deployment, or if it needs a little bit more work. Importantly, these metrics usually only measure generative performance, but as an investor or a founder, you need to be aware of other costs, other performance metrics: inference cost, storage cost, deployment cost, the cost to train this model, the checkpoints, wall clock time, GPU reliability, and much more. Even though these details are tricky, the high-level concepts are fairly straightforward. You need a dataset, you need a model, and you need a way to measure the performance, and you need more than a few GPUs. I think that's enough to get you started and start delivering value to your customers and clients.